Important random variables. Bernoulli random variable. This is a discrete random variable taking two values 1 and 0 with probabilities p and 1 minus p. Binomial random variable. This is a discrete random variable giving the number of ones in a sequence of n independent Bernoulli trails. The PMF is given by p of x equal to k equal to nck p power k 1 minus p whole power n minus k for 0 less than or equal to k less than or equal to n. nck p power k 1 minus p whole power n minus k 0 less than or k less than or equal to n 0 otherwise. This random variable models the total number of bits received in error when a sequence of n bits is transmitted over the channel with bit error probability p. Uniform random variable. This is a continuous random variable taking values between a and b with equal probability or intervals of equal length. The density function is given by fx of x equal to 1 by b minus a less than or equal to x less than or equal to b, 0 otherwise. When the phase of a sinusoid is random, it is usually modeling as a uniform random variable between 0 and 2 pi. Gaussian or normal random variables. This is a continuous random variable described with a density function fx of x equal to 1 by root over 2 pi sigma square e power minus of x minus m whole square by 2 sigma square. M means mean of random variable, sigma means standard deviation. Gaussian random variable is the most important and frequently encountered random variable in communications. CDF for the Gaussian random variable with m equal to 0 and sigma equal to 1 is denoted by phi of x and given by phi of x equal to p of x less than or equal to x equal to integration of minus infinity to x 1 by root 2 pi e power minus t square by dt square dt, whatever it may be. A closely related function is q of x equal to 1 minus phi of x. The function is well tabulated and frequently used in communication q of x, which satisfies the following relations. Q of minus x equal to 1 minus q of x equal to q of x. Q of 0 equal to 1 by 2, q of infinite equal to 1. For a Gaussian random variable having mean and distributed standard deviation or p of x greater than x equal to q of x minus m by sigma. The q function is related to erroneous functions ERFC of x equal to 2q root 2x or q of x equal to half into ERFC of x by root 2. Distribution functions. Uniform PDF f of x equal to 1 by b minus a less than or equal to x less than or equal to b, mean a plus b by 2, variance b minus a whole square by 12. Normal or Gaussian f of x equal to 1 by root 2 pi sigma square exponential of minus half x minus m whole square by 2 sigma square, mean m, variance sigma square. Poisson f of x equal to p of x equal to k equal to lambda power k into e power minus lambda by k factorial, mean lambda, variance lambda. Binomial f of x equal to p of x equal to k equal to nck p power k 1 minus p whole power n minus k, mean np, variance np into 1 minus p. Bernoulli f of x equal to p for k equal to 1 minus p for k equal to 0 where 1 minus p equal to q, mean equal to p, variance equal to p into 1 minus q that equal to pq. Realize f of x equal to 1 by sigma square e power x minus x square by 2 sigma square, mean equal to sigma into root pi by 2, variance equal to 4 minus pi by 2 into sigma square. Function of a random variable. A function of a random variable y equals g of x is itself with a random variable. Then pdf of the random variable y in terms of pdf of x is fy of y equal to sigma I fx of xi by c dash of xi, where xi is a countable number of solutions of equation g of x equal to y. Statistical averages. Expected values of random variable x is defined as g of x equal to integration of minus infinity infinity x into f of x dx. Then the order moment of a random variable x is defined as e power of x power n equal to integration of minus infinity infinity x power n fx of x dx. Expected value of y equal to g of x is e of y equal to integration of minus infinity infinity g of x fx of x dx. For discrete random variables, x expected value of x is e of x equal to sigma I xi p of x equal to xi e of g of x equal to sigma I g of xi p of x equal to xi. Properties of expected value use the expectation of cx equal to c into e of x, where c is a constant, e of c equal to c, e of x plus c equal to e of x plus c. Variance, it is defined as e of x minus e of x whole square equal to sigma square equal to e of x square minus e of x whole square. Variance represents AC power content of random signal. Properties of variance of c of x equal to c square, variance of c equal to 0, variance of x plus c equal to variance of x. Characteristic equation of a random variable x is denoted by psi x of v and defined as psi x of v equal to integration of minus infinity to infinity fx of x e power j vx dx. To obtain nth moment of the random variable x, the relation is mx of power n equal to 1 by j power n d power n by dv power n psi x of v for v equal to 0. Multiple random variables joint CDF for two random variables x and y is given by fxy of xy equal to probability of x small less than or equal to small x or capital Y less than or equal to small y. Joint PDF is defined as fxy of xy equal to dou square by dou x dou y fxy of x comma y. Conditional PDF of random variable y gives that value of the random variable x is equal to x is denoted by fy by x of y by x and is defined as f of fy by x of y by x equal to fx comma y of x comma y by fx of x, where fy of x is not equal to 0 otherwise the expected value of gxy, where gxy is a new function of x and y is obtained from e of g of xy equal to integration of minus infinity infinity integration of minus infinity infinity g of xy fxy xy dx dy. The special case where gxy equal to x minus mx into y minus mx, we obtain a expectation of g of xy equal to e of xy e minus mx my, which is called covariance of x and y. Here mx and my are expected value of x and y. Covariance of xy equal to expectation of xy minus e of x into e of y. Covariance of xy equal to e of xy minus e of x into e of y. The normalized version of the covariance is called correlation coefficient and is denoted by rho of x comma y and is defined as rho of x comma y equal to correlation COV of x comma y by sigma x sigma y 0 less than or equal to pxy less than or equal to 1. If x and y are independent random variables, then the covariance of xy equal to 0. But if rho of xy equal to 0, it does not imply any necessary that random variables are independent. Variance of sigma I ci xi equal to sigma I ci square, variance of xi plus sigma I sigma j is not equal to I ci cj covariance of xi comma xj. Let z be a random variable defined as z equal to x plus y, where x and y are uncorrelated. Variance of z equal to variance of x plus variance of y plus 2 covariance of x comma y. Basic properties of joint PDF and CDF. Fx of x equal to fxy x comma infinity, fy of y equal to f of x comma y of infinity comma y. Fx of x equal to integration of minus infinity infinity fxy xy dy, fy of y equal to integration of minus infinity infinity fxy xy dx. Integration of minus infinity to infinity integration of minus infinity infinity fxy x comma y dx dy equal to 1. fxy x comma y equal to integration of minus infinity to x minus infinity to y fxy u comma v du dv. Multiple functions of multiple random variables. If we define two functions of the random variable x and y, z equal to g of xy, w equal to h of xy, the joint PDF of z and w is f of zx comma z and w equal to sigma I f of xi yj by determinant of j of xi yi, where Jacobian g of x comma y equal to dou z by dou x, dou z by dou y, dou w by dou x, dou w by dou y. Xi and yi are the solutions of two equations given as 1 and 2. Central limit theorem. This theorem says that sum of random variables which generally occur in practical systems takes the form of Gaussian random variable. Random processes. Random processes is a collection of time functions or signals corresponding to various outcomes of a random experiment. Random process is a collection of time functions or signal corresponding to various outcomes of a random experiment. Autocorrelation function. This represents the relation of a function with its shifted version. The autocorrelation function of the random process x of t, denoted by rxx of t1 t2, is defined as rxx of t1 t2 equal to expectation of x of t1 into x of t2. Stationary process, a process whose statistical properties are independent of choice of time origin, is called stationary process. The process x of t is called White's stationary if the following conditions are satisfied. Mx of t equal to expectation of x of t is independent of t. Rxx of t1 comma t2 depends only on the time reference tau equal to t1 minus t2 and not on t1 and t2 individually. Mx of t and Rxx of t plus tau comma t are periodic with period t. Then process is called cyclostationary process. Properties of autocorrelation function Rx of tau. Rx of tau is an even function, that is Rx of tau equal to Rx of minus tau. The maximum absolute value of Rx of tau is achieved at tau equals 0. That is Rx of tau less than or equal to Rx of 0. If for some t naught we have Rx of tau now t naught and Rx of 0, then for all integers k Rx of k t naught equal to Rx of 0. Rx of 0 gives power content of a power signal. Rx of 0 gives energy content of a signal. If a signal is energy signal, Fourier transform of Rx of tau gives power spectrum density for power signal, energy spectrum density for energy signal. Power and energy of a random signal. Power content of a random signal x is given by px equal to e of limit t tends to infinity 1 by 2 to integration of minus t to t x square t dt equal to px equal to limit t tends to d infinity 1 by 2 t integration of minus t to t expectation of x square t dt. Px equal to limit t tends to infinity 1 by 2 t integration of minus t to t rx of t comma t dt. Energy content of a random signal is given by ex equal to expectation of integration of minus infinity infinity x square t dt equal to x equal to integration minus infinity infinity rx of t comma t dt. For the case of stationary processes, only power type process is of theoretical and practical interest. Cross correlation function between two random variables x of t and y of t is rxy of t1 comma t2. Expectation of x of t1 into y of t2 rxs of rxy of t1 comma t2 equal to ryx of t2 comma t1. Random processes and linear systems x of t lta h of t y of t. Let random process x of t is input to an lta system having impulse response h of t and y of t is output of lta system. Then if x of t is stationary process, then x of t and y of t will be jointly stationary with expectation of y of t equal to expectation of x of t into integration of minus infinity infinity h of t dt. Rxy of tau equal to Rx of tau convolution with h of minus tau. Ry of tau equal to Rx of tau convolution with h of minus tau convolution with h of tau. Sy of f equal to x of x x of f into h of f square. Sy of f equal to x of f into h of f square, whereas x of f sy of f is nothing but power spectral density of input and output process. Power spectral density of a random process x of t is given by sx of f equal to f of rx of tau. If the two random processes x of t and y of t are uncorrelated, then rxy of tau equal to ex of comma t into ey of comma t, where x of t and y of t are jointly stationary processes. Now comes under pulse modulation techniques. Pulse analog modulation technique. Pulse analog modulation techniques are of three types, namely PAM, PWM, and PPM. PAM, in this modulation scheme, amplitude of a high frequency carrier is varied in accordance with the sample values of message signal. Time domain representation of PAM is shown in figure, where M of t is message signal, C of t is carrier signal, and S of t is PAM modulated signal. Pulse width modulation. In this modulation scheme, width of the carrier pulses are varied in accordance with the sample values of the message signal. Time domain representation of PWM is shown in figure. Speed control of DC motor is done using PWM. Pulse position modulation. In this modulation scheme, position of high frequency carrier pulses is changed in accordance with the sampled values of message signal. Time domain representation of PPM is shown. PWM is generated using triple five timer in monostable multivibrator mode. PPM is generated using triple five timer by using PWM as a trigger signal in monostable multivibrator mode. Comparison of PAM, PWM, PPM. PAM bandwidth is less, PWM bandwidth is high, PPM bandwidth is high. PAM power efficiency lowest, PWM power efficiency moderate, PPM bandwidth power efficiency highest. PAM complexity lowest, PWM complexity moderate, PPM complexity highest. PPM PPM is most effective pulse analog modulation scheme in terms of SNR, pulse distillation modulation techniques, important pulse distillation modulation techniques or pulse code modulation, PCM, delta modulation, differential pulse code modulation, PCM. In this modulation scheme, we first sample the analog signal, then quantize it to convert into levels and encode it to then send it in the form of digital codes. If there is n bit quantizer and sampling rate is fs, then bit rate will be rv equal to nfs bits per second. Sampling must be done at rate greater than or equal to Nyquist rate in order to avoid aliasing. Higher we will be sampling rate, easy will be reconstruction of signal at receiver. Bandwidth requirement is minimum RB by 2 and maximum RB. If uniform quantizer with step size delta is used, delta equal to Vmax minus Vmin by L equal to Vmax minus Vmin by 2 power n, where L is number of levels, then maximum quantization error will be delta by 2. Normally used uniform quantities are mid-thread type and mid-rise type. Quantization noise power for uniform quantization equal to del square by 12. Quantization noise power for uniform quantization equal to del square by 12. Signal to quantization noise ratio for PCM for sinusoidal input is for uniform quantizer SNRQ equal to 6n plus 1.76 dB, where n is number of bits of quantizer. Signal to quantization noise ratio for PCM for uniformly distributed random variable SNRQ equal to 6.02n. Yes, number of bits of quantizer increases, SNRQ increases, but at the same time bandwidth requirement for transmission also increases. Compounding is the compression of signal at transmitter end and expansion of signal at receiver end. There are two types of compounding techniques: Euler compounding and Euler compounding. Euler compounding means modulus of V out equal to natural log 1 plus mu of modulus of Vn by natural log 1 plus mu, where mu max equal to 255. Euler compounding modulus of V out equal to A into modulus of Vn whole by 1 plus A for 0 less than equal to modulus of Vn less than equal to 1 by A. 1 plus natural log A modulus of V in by 1 plus natural log A for 1 by A less than or equal to modulus of V in less than or equal to 1, where A max equal to 87.6. Compounding is done to avoid nonlinear distortion of channel. Compounding is widely used in telephone systems to reduce nonlinear distortion and also to compensate for signal level difference between soft and loud talkers. Differential pulse code modulation. When the samples of a signal are highly correlated, then we go for DPCM in order to save bandwidth or using the same bandwidth, higher data rate. DPCM principle used is prediction. Delta modulation is a special case of differential pulse code modulation. Delta modulation is called 1 bit DPCM as it transmits only 1 bit per sample. Delta modulation problem of slope overload occurs if input is changing very fast, that is modulus of del by Ts is less than modulus of dm of t by dt. Slope overload error occurs. Slope overload occurs. To overcome slope overload error, we choose optimum size of delta such that delta of optimum by Ts equal to modulus of dm of t by dt max, where Ts is sampling time. For m of t equal to am cos 2 pi fm t, delta of opt by Ts equal to 2 pi fm am. Second type of error is granular noise hunting, which occurs when mass is almost constant. SNR of max equal to 3 by 8 pi square into fs by fm whole cube. fs by fm మాత్రమే క్యూబ్ వస్తుంది, where fs is sampling frequency, fm is message bandwidth. Adaptive delta modulation. In adaptive delta modulation, step size is chosen in accordance with the message signal sample value to overcome slope overload error and hunting. If message is varying at a higher rate, then step size is high, and if message is varying slower, then step size is small. Multiplexing. There are many types of multiplexing, out of which two are FDM and TDM. In FDM, we divide whole bandwidth of channel in small segments and allot it to different users so that they can access channel at the same time by using their allotted bandwidth. In TDM, whole time slot is divided among different users so that at a time only one user is accessing the channel. Bandwidth requirements in TDM and FDM is almost same for same number of users. If we are using TDM plus PCM, then there are n messages having same bandwidth and the sample rate fs, then bit rate will be RB equal capital N into small n into fs, where n equal to bits in quantizer. If the bandwidth of message and sampling rates are different, then overall bit rate will be RB equal to RB1 plus RB2 plus RB3 and so on RBN, where RB1, RB2, RB3 and so on RBN are bit rate of respective messages. Bandwidth requirement, if raised cosine pulses having rolling roll of factor alpha is used, bandwidth equal R naught by 2 into 1 plus alpha, where alpha lies between 0 and 1. In case of ADM and DM, bandwidth requirement is almost same. Amplitude digital modulation schemes దాంట్లో ASK amplitude shift key. In this scheme, amplitude of a high frequency carrier is varied in accordance with the digital data 0 or 1. For digital input 1, amplitude level is high, and for digital input 0, amplitude level is low. Signaling use is on-off signaling. Bandwidth requirement for ASK is bandwidth equal 2 by TB equal to RB. In ASK, probability of error PE is high, SNR is less. Frequency shift keying. Frequency of carrier is varied in accordance with digital data 1 or 0. For digital data 1, we use frequency F1. For digital data 0, we use frequency F2. Normally, F1 greater than F2. NRZ signaling is used. Bandwidth requirement in case of FSK is bandwidth equal to 2 RB plus F1 minus F2. In case of FSK, PE is less and SNR is high. Multiplexing is difficult, used in modems. Phase shift keying. In phase shift keying, phase of high frequency carriers vary in accordance with the digital data 1 or 0. NRZ signaling is used. Bandwidth requirement for PSK, bandwidth equal to RB equal 2 into bit rate. In the case of PSK, probability of error is less, SNR is high. Mainly used technique is wireless transmission. Complexity of coherent schemes is always high compared to non-coherent schemes. Coherent schemes have less probability of error compared to non-coherent schemes under same conditions. ASK scheme has lowest noise immunity against noise. PSK is best among all shift keying schemes. Coherent schemes requires lesser power compared to non-coherent schemes for same probability of error. MRS signaling. In MRS signaling, we use M number of phases in case of PSK, M number of frequencies in case of FSK, M number of amplitudes levels in case of ASK for sending digital data. By using MRS scheme, we can send data at higher rate at the expense of increased probability of error. Bandwidth requirement for MRS scheme is bandwidth equal bandwidth of binary scheme by log m base 2. For MRI PSK, bandwidth equal 2 RB by log m base 2. Baud rate is the data rate, the output of the modulator. Baud rate is given by baud rate equal to bit rate by log m base 2. Next one is QAM. In QAM, digital information is contained in both amplitude and phase of the signal. It is used in both digital modulation schemes and analog modulation schemes. In cable television and in cable modulation applications, QAM is used. Noise in digital communication for better SNR matched filter is used, whose impulse response h of t equal s conjugate of tb minus t, where conjugate represents complex conjugate. TB means bit duration, s of t means input signal to filter. Probability of error PE equal q of root over differential energy square by 4 into noise spectral density. PE equal to q into root over ED by 2n naught, where ED equal to integration of TB S1 of t minus S2 of t whole square dt, where n naught by 2 is two-sided noise power spectral density. Q of x equal to half into Arrhenius function of x by root 2. Q of x equal to 1 by root 2 pi x square e power minus x square by 2. Probability of error for differential PSK is half into exponential of minus half AC square TB by 2 n naught. In case of FSK, F1 and F2 are chosen such that F1 equal to MFS and F2 equal to KFS, where M, K are integers. Bandwidth efficiency of for PSK is BE, bandwidth efficiency equal to transmission rate by bandwidth of signal at output, RB by 2 RB equal to 0.5. Comparison of digital modulation schemes system. Coherent ASK S1 and S2, S1 of t equal to a cos omega ct, S2 of t equal to 0. Its bandwidth is 2 RB. Its probability of error PE equal to q into root of AC square TB by 4 n naught. Non-coherent ASK S1 of t equal to a cos omega ct, S2 of t equal to 0. Bandwidth is 2 RB. Probability of error PE equal to half into exponential of minus AC square by 8 n naught. Coherent FSK, S1 of t equal to A cos 2 pi F1 t, S2 of t equal to A cos 2 pi F2, bandwidth equal to 2 RB plus F1 minus F2, probability of error Q of root over AC square TB by 2 N naught. Non-coherent FSK, S1 of t equal to A cos 2 pi F1 t, S2 of t equal to A cos 2 pi F2 t, bandwidth is greater than 2 RB, PE equal to half into exponential of minus AC square by 4 N naught. Coherent PSK, S1 of t equal to A cos omega ct, S2 of t equal to minus A cos omega ct, bandwidth equal to 2 RB, probability of error equal to Q into root of AC square TB by N naught. Non-coherent PSK, S1 of t equal to A cos omega ct, S2 of t equal to minus A cos omega ct, bandwidth equal to 2 RB. Information theory. Information content in a signal will be high if probability of its occurrence is less. If probability of occurrence of message is p, then its information content I will be I equal to log base to 1 by p bits, where I equal to log 10 base 10 1 by p Hartley or decit, I equal to natural log 1 by p nat. Entropy, average information content per symbol in a group of symbols, is known as entropy and represented by h. If you have m symbols with probability of occurrences of p1, p2, and so on, pi, pm, then entropy h will be h equal to sigma I equal to 1 to m pi log base to 1 by pi bits per symbol. Entropy will be maximum. It probability of occurrence of all m symbols will be equal, and h max equal to log m base to bits per symbol. Source information rate, if source is emitting symbols at a rate r symbols per second, the source information rate r is given by r equal to rsh bits per second. What are the source encoding techniques? Fixed length coding, variable length coding, Shannon-Fano coding, Huffman coding. Efficiency of Huffman coding is high as compared to Shannon-Fano coding. Channel coding. What are the channel coding techniques? Hamming coding, convolution coding. Source coding is done for data compression in order to transmit it more efficiently. Channel coding is done to reduce probability of error. Efficiency of encoding techniques. Efficiency is given by eta equal to h by L, where h is entropy, L bar is the average number of bits per symbol according to encoding techniques. Types of channel: discrete memoryless channel, x1, x2, and so on, xn. Channel P of y by x equal to y1, y2, and so on, ym. P of y by x equal to P of y1 by x1, P of y2 x2, and so on, P of yn xn. P of y1 by x2, P of y2 by x2, and so on, P of yn by x2, P of y1 by x1, P of y2 by xn, and so on, P of yn by xn. Channel matrix: P of y equal to P of x into P of y by x. Sigma equal to 1 to m. P of xi yj equal to P of yj marginal probability. P of xy equal to P of xd into P of y by x joint probability. P of xd is the diagonalized form of P of x. Binary symmetric channel: x1, y1, x2, y2, x1, y2, x2, y1, x1 to y1 at 1 minus p, x1 to y2 at p, x2 to y1 to p, x2 to y2 means 1 minus p. P of y by x equal to 1 minus p, p 1 minus p. Mutual information of two random variables is measured how much one random variable tells about others. I of xy equal to h of x minus h of x by y. H of that equal to h of y minus h of y by x bits per symbol. H of xy equal to h of y by x plus h of x, h of x by y plus h of y. Channel capacity. Capacity of a channel is defined as maximum data rate that can be supported by channel with minimum probability of error. Cs equal to I of x y max bits per symbol. Channel capacity for binary symmetric channel is Cs equal to 1 plus p log base to p plus 1 minus p into log base to 1 minus p bits per symbol. Entropy relations: h of x equal to minus sigma I equal to 1 to m p of xi log base to p of xi equal to integration of minus infinity to infinity f of x log base to fx of x dx. H of y equal to minus sigma j equal to 1 to n pyj log base to pyj equal to minus infinity to infinity p of y log base to fy of y dy. H of y by x equal to minus sigma I equal to 1 to n sigma j equal to 1 to n p of xi comma yj log base to p of yj by xi. Integration of minus infinity to infinity minus infinity to infinity infinity to infinity fxy xy log base to fy y by x dx dy. h of xy equal to minus of sigma I equal to 1 to m, sigma j equal to 1 to n, pxi y log base to p of xi yi, that equal to integration of minus infinity infinity minus infinity infinity fxy xy log base to fxy xy dx dy. Channel capacity of AWGN channel, capacity of a channel having bandwidth be added to Gaussian band limited as white noise is C equal B log base to 1 plus S by N bits per second. This is Shannon-Hartley theorem. Here B is bandwidth of channel. C equal to B log base to 1 plus S by N bits per second, where B is tending to infinity, then capacity does not become infinity as S by N tends to 0 due to high noise power. So limit B tends to infinity, C equal to 1.44 into S by N naught, where S is signal power, N naught by 2 means two-sided noise spectral density. Error codes. Error control codes when a signal is transmitted through channel. The probability of error or a particular signaling scheme is function of signal to noise ratio at receiver input information rate in practical systems. Maximum signal power, the bandwidth of channel, and noise power spectral density eta by 2 are fixed for particular environment using signaling scheme. It is not possible often to achieve acceptable probability of error. Therefore, error control coding is used to achieve required minimum probability of error. ARQ, methods of error correction are ARQ, FEC. ARQ means automatic repeat request. When an error is detected, a request is sent to transmitter from receiver to retransmitter signal. It needs a duplex arrangement. Time delays are involved due to request and repeat signals. Therefore, it cannot be used in real-time signals, where FEC stands for forward error correction, an automatic mechanism of error correction in the form of error correction code is employed, and hence no retransmission occurs. It needs simplex arrangement, no delays are involved, hence it can be used in real-time signals. Simplex duplex transmission. Parity check. Parity check code, when the number of check bits is 1, it is known as parity check code. Is of two types: even parity check code, if its check bit is such that the total number of ones in the error code, the code word is even, it is even parity check code. Odd parity check code, when the check bit is such that total number of ones in code word is odd, it is called odd parity check code. Message 010011, code for even parity check bit 1, code for hard parity check bit 0, 101110, code for even parity check bit 0, code for odd parity check bit 1. If a single error occurs in the same message, it can be easily detected as it changes the number of ones from even to odd or from odd to even. Important definitions: code word, it is block of bits in the output of channel encoder. Code rate, R equal to number of bits in message blocked by number of bits in encoded for code word. K by N is less than or equal to 1. RB means bit rate before channel encoding equal to 1 by TB. R equal to bit rate or channel data rate after channel encoding equal to 1 by T naught. KTB equal to NT naught. R naught equal to N by K into RB, that equal to RB by small r. R naught is greater than equal to RB. Once again, R naught is nothing but bit rate or channel data rate after the coding, channel coding equal to 1 by T naught, KTB equal to NT naught, R naught equal to N by K, RB that equal to RB by R.